We have another great session here. I won't take up too much of your time. We're looking to get right into it. We have Paul Kealey here from EcoBuilt, and he's looking to chat about achieving pH standards in challenging conditions across North America. So with that, I'll hand over the mic and give it to Paul.
Okay, great. So the title of this presentation, Defy the Odds. Defying the Odds. Something to keep in your mind throughout this whole presentation, because defying the odds of Passive House is going to mean something a little bit different for all of us. But again, it's great to be here. You know, after walking around, I kind of feel like we're at a giant Passive House party. One where we get to celebrate gaskets, talk about high performance windows, and the thrill of a really well-sealed air barrier detail. And if there's one thing this room has in common, it's that we're the only crowd that genuinely gets excited by our values in thermal bridges. Like, this is our Super Bowl, isn't it? But instead of touchdowns, we're celebrating air tightness. And we don't talk about our homes like homes. We talk about them like Olympic athletes. Like, yeah, mine hit a 0.3 ACH 50 on the first try with no steroids either. But jokes aside, most importantly, we're here to discuss a house of change and how it can make the most impact in this world that we're living in today. So let me ask you this. Why are you here? Not just at this conference, but in the Passive House world itself. Are you a builder, an architect, a student, a policymaker possibly, the government? Or maybe you just wandered in here thinking it was the line for the washroom and you stayed because it felt really airtight. So for all the veterans in this room, what keeps you going? And for all the newcomers, what drew you in? Whatever brought you here, know this: by simply showing up, you're already part of something that defies the odds. You're part of a movement that's reshaping the very idea of the home. What it means, how it's built, and who it's built for. Whatever brought you here, know this: simply by showing up, you're already a part. You've chosen the path less traveled, the one lined with blower door tests, certification spreadsheets, and endless debates about thermal bridging that sometimes ruin family dinners. Passive House isn't just the house of high performance. This is the house of change. For me, it's a house that's designed for a self-sustainable world. The only type of house that really makes sense from a net zero perspective. But we'll get more into that later. Now, I've been in the sustainable housing world for over 20 years now. But it didn't begin with a blueprint for me. It began with a blackboard. I was a teacher. I believe that knowledge should lead to action. But let's be honest. There's only so much action you can spark by grading science tests. So when I was a teacher, I thought I had it made really at 23 years old. I went out looking for a house to buy. So I educated myself. I looked at all the options. What was out there? Old homes, newer homes. I went into them all. And I read about R2000, didn't know so much at the time, but I also remember reading about sick building syndrome. And this led me to the idea of creating a healthy home, because every house I went into, something just didn't feel right. Something to do with the indoor air quality. So I did some research, and at the time I felt that a log house was the best sustainable home, the healthiest home. And when you think about a log home, a home with natural, non-manufactured materials, there's no healthier house. So this caused my switch. I left teaching. I did some more research, found out that over half of the handcrafted log builders in the world are here in Canada, in British Columbia in particular. So I moved out west, learned how to build, came back to Ottawa a couple years later, with the intention of starting a log home company. But at the time, there was a problem. We were going through a major recession at the time. I thought, part of me thought, great time to start a business. Everyone's getting out of the business. I'm getting into the business. But that wasn't the case. There was no work. I had to go out and find the work. So ironically, I ran into someone named Hjalti from Iceland. Now, if anyone's been to Iceland, you know there's probably enough trees on that whole island to build a single log home. But young Hjalti was starting his log home business, and Icelanders, you know, they're really connected to their past. They love natural buildings, and there's no stronger building than a log home. So ultimately, this is where I fell in love with the purpose of the home. The purpose to protect generations. The purpose of the home really designed to last an infinite amount of time. But I think it also has something to do with the harsh climate Icelanders deal with. You know, I can remember Hjalti telling me, Paul, it blows over 100 kilometers an hour here often. And we expect rain to be driven upwards on a 60-degree angle. So sealing the house is very important. So ultimately, that's when I fell in love with the art of sealing the house. So I moved home, came back to Ottawa, and really felt I had done a good thing, made the right decision. We built our demonstration model log home here. And then a few years went by, and we end up with a bigger problem, the energy problem. Log homes take a lot of energy to heat. And this isn't such a big deal in Iceland. You know, homes in Iceland, they have a hot water line coming in through the foundation, just like a cold water. That country is sitting on a giant hot spring. So energy, renewable energy is plentiful, it's available, it's cheap. That's not such the case in Canada. When we built our demo house, our log home, between 2008 and 2012, you know, like this is when I defined we started to go through our energy crisis. I seen our hydro bills go from $50 a month in the winter to over $400 using an electric boiler. Never wanted to heat that log home with petroleum-based fuels. So ultimately, at this point, I reevaluated what's the best sustainable home. And ultimately, it's one that uses little energy, low energy, or conserves as much energy as possible. Did some more research, and ultimately, this is what caused me to fall in love with the passive house concept, the ultimate low energy building model, the place where science meets soul, where performance becomes purpose. Because this isn't just about building better houses, it's about building homes that belong in a self-sustainable world. Not just sustainable, but self-sustainable. Now, sustainability, by definition, lots of you probably know, means meeting the needs of the present without compromising the future generations' ability to meet their own needs. Now, this sounds very noble, but it's basically a polite way of saying, let's try not to make things worse. Now, in a world that's already compromised, that's not good enough. Self-sustainability is a different mindset. It doesn't settle for less harm. It demands more good. A truly self-sustainable home is like a well-rooted tree, built to last, drawing only what it needs and giving more than it takes. Made from renewable materials and needing so little energy, even a small, affordable solar array becomes a powerhouse of independence. It doesn't just survive, it belongs. So today I want to show you what it looks like to defy the odds, not by waiting for change, but by building it. So let's get into it. The problems. The carbon problem. Now, Bill Gates puts it most simply. Excess carbon in the atmosphere leads to temperature increase, which leads to negative effects. Now, most non-passive buildings, as we all know, are gas guzzlers. But there's also lots of net zero homes being built that are consuming gas as well. And that's a problem. And this problem can be simply and easily avoided today by building passive. Due to the ultra low energy demand, very simple to be carbon free. After all, every ton of carbon that we don't emit is one that we never have to offset, capture, or apologize for. So passive house instantly solves a carbon problem. The resiliency to weather problem. Weather issues, changing weather patterns becoming much more prevalent. Now, passive house, as we all know, demands thicker building envelopes. So there's a lot of simple opportunity to integrate. And you know, with the demand of passive homes, the requirements for fully integrated air barriers, vapor barriers, water barriers. There's a lot of extra opportunity to make the house stronger. Passive house instantly solves the resiliency to weather problem. Power outages are also becoming more prevalent. Resiliency to power outages. Very simply solved by passive house. We probably remember, if you remember a few years ago, it might have been 2 years ago, down in Texas, the Gulf Stream dipped down, which has become more often. Just for a few days, I believe, houses as far as Austin, Texas in the south experienced massive problems. Pipes were bursting all over the place, millions of dollars of damage. Now, we, as a company, we know our demonstration home is located here in Ottawa. We have some direct experience with our demonstration home being vacant for weeks at a time during a freezing cold Ottawa winter. We monitor the temperature, and the temperature has never dropped below 13 or 14 degrees Celsius, with even in polar vortex conditions, minus 35 conditions. So passive house instantly solves the resiliency to power outage problem. The energy problem. Of course, we know this is a big problem. Rising energy costs keeps rising because of high production, a high demand, so we need to build to conserve. And passive house is a house like no other when it comes to energy conservation. We also know from our demonstration home that the total cost for heating, also cooling in Ottawa, a certifiable passive house will cost less than $200 to $250 a year using a heat pump for all heating and cooling purposes. So passive house instantly solves the energy problem. The health and comfort problem. Now, as Canadians, we can all relate to this. We spend about 90% of our time indoors in the wintertime. Non-passive buildings that experience a lot of air leakage ultimately are letting a lot of toxins into the home through leaky building envelopes. And we also all know where warm air meets cold air, we get condensation. What happens when condensation happens in a building envelope? Mold occurs. Mold is inevitable in non-passive buildings. I've heard buildings as young as 3 to 4 years old really experiencing mold problems today. So it's a big problem. And passive house solves against this by airtight building assemblies, preventing those toxins from coming into the home. This is very important in forest fire prone areas. And requirements, a standard requirement for a passive certifiable building envelope to be vapor open permeable. So open permeable membranes mitigate that moisture. And when you can mitigate the moisture and build airtight, now you're in a building that basically has zero chance of mold growth. So very healthy. From a comfort perspective, it's a great thing that building codes now, Canadian codes, are starting to demand ERV machines, fresh air machines. But there's a big difference between a non-passive ERV machine and a passive one. Non-passive machines, I believe, are anywhere from 50 to 70% efficient at 0 degrees Celsius. The passive ERV machines are going to be 75 to 90% efficient at minus 15 degrees Celsius. And that's a big deal. You know, the difference is the air coming into the living spaces with a passive machine is 17 degrees or above, so that's a comfort criterion. And non-passive machines, that air coming into those vents is anywhere from 5 degrees to 10 degrees Celsius. When it's cold outside, that's a very uncomfortable situation. So passive house really solves against the health problem. The resources problem highlights the need. We really need to focus on regenerative materials, ones with high renewable, high recycled material content for sustainable resources. Ultimately, use renewables, conserve non-renewables. Now, a great example of conservation, for those of you that don't know, is Lake Mead. Lake Mead is the largest reservoir in the United States, and it supplies millions of people with fresh water. Also supplies millions of people with electricity through the Hoover Dam, hydropower. And is also responsible for irrigating millions and millions of acres of agricultural land. As levels drop, this water is reducing its 30% capacity. Conservation is a huge deal. Also, another example to highlight here. Arctic ice is known to be declined by about 35%. Now, the Arctic ice sheet is known to be Earth's mirror, reflecting about 80% of the energy, sun's energy, back into the atmosphere. So as this ice melts, our darker oceans are absorbing a lot more of that energy, which is accelerating global warming, of course. We've all heard about it. And more heat that's absorbed by our oceans leads to thermal expansion, which is the reason why sea level is going to be rising. And if this continues, in the year 2100, it's estimated over 400 million, almost 500 million people are going to be displaced, including New York City. Now, luckily, the government knows that we have all these problems to deal with. And thank God, Canada, I believe, along with 250 other countries in the world, have committed with mandated net zero legislation. So less than 5 years ago. Okay, but, knowing this is no joke. The joke is there's still no incentives for building net zero, and there's no compulsory building code programs that are really moving towards net zero to achieve our goals. And when I think about it, it's just kind of like, the incentives that do exist out there. There is an incentive program, but that program is to essentially incentivize someone for removing their old furnace and replacing it with a new furnace. Okay, when I think of that, I think of it's like bailing water out of a sinking boat. It's a Band-Aid to the solution. We need to stop funding upgrades to the problem and start investing in the solutions. So this is a call to action. Heard the keynote this morning. We need to, if there's no more important time to band together, talk to our MPs and everyone be a voice so that just change happens finally once and for all. So here, just a little bit of a break. I like to try something different. And for everyone, if you're a little comfortable, I'd like you to close your eyes for a moment and think of defying the odds. Think of self-sustainability. And imagine what a truly self-sustainable world looks like for you. What do you see? How do the buildings look? How does it feel to live there? What is your relationship to energy, to nature, and to your home? Now picture the world built around you, the city, the suburbs, your neighborhood. What would it look like if it was completely transformed? Not just efficient, but regenerative. Not just consuming less, but giving more. Now you can open your eyes, if you haven't already. This world isn't a fantasy. It's closer than we think. And to understand how we get there, we need to understand where we've been. And, except for recent times, we have always been self-sustainable. Let's take Ottawa, for example. A picture in the top left, Chaudière Falls, a very short walk from here. Used to provide renewable electric energy for the Ottawa rail car, the streetcars that were in Ottawa for over 70 years. From the late 1850s to about 1960, 100% renewably operated streetcar. Then oil came around, dominated the world. We lost our ways. We turned to gas. That's why the buses are here and haven't left. But, a great example, we're getting back. The O train in the top right is an example. Sustainability is returning. Thank God. Just needs to move quicker. You can see a picture of the logger at the middle in the top. Ottawa Valley loggers. Great stories. These people, these guys are not sustainably hearted individuals at all. But they know in order for them never to have to replant their woodlots, all they need to do is selectively harvest the trees. Only cut so many trees down in a particular area, and the woodlot will naturally regenerate itself. So a great story of sustainability. Human instinct has always been around self-sustainability. It just makes sense. A couple examples of the natural world, the instincts of the natural world. The termite mound. The termite mound has been known as the HVAC marvel of the natural world. Termites need to keep the inside environment of these mounds very stable, 30 degrees Celsius, almost 100% humidity year-round, despite harsh exterior climate, very hot days, cold nights, and they do this without fans, ducts, or thermostat, just instinct. Brilliant design, a combination of ventilation towers, porous walls, lots of tunnels and chambers. They're actually able to restrict the airflow at night when it's cool, and really, do a lot of tunneling to keep the humidity with porous walls from almost 100% nonstop. Also, beavers. Beaver lodges stay above freezing. Beavers are known as passive house pioneers. Even when it's been documented minus 35, minus 40 degrees Celsius, the inside of a beaver lodge is above 0 degrees, simply by the heat from a family of beavers. Airtight construction and building the walls thick enough to create that environment. Beavers don't build to code, they build to survive. They nailed passive before passive was cool. Instincts of our past human world. Let's look at the Inuit, indigenous communities, very similar to the beaver. Built dome-like structures, and the inside of these igloos have been known to be above 10 degrees Celsius, somewhere between 10 to 15, with a family of people inside. Our bodies, everyone's is different, but our bodies are known to be the equivalent of anywhere from a 60 watt to 100 watt light bulb. And it's just a matter of building the igloo with thick enough walls. When you look at the igloo, the geodesic dome structure, one of the best surface area to volume ratios when it comes to it. When you look at the geometry of a geodesic dome, surface area to volume is really incredible how low it is. So basically an example how the Inuit used instinct to not only build thick enough walls efficiently, but the shape of the building, they just understood it through natural instinct. Darius, the Greek architect, 2,500 years ago, designed entire cities with passive solar principles in mind. Homes are oriented to face south, capturing the sun's warmth, staying shaded in the summer also with very thick overhangs and thermal mass to regulate temperature. Ancient Greece wasn't in the same climate as the Inuit, so survival wasn't as necessarily important for Darius, but comfort was. Comfort for his people was very important. And that brings us to the modern world. The instinct of the modern world, the instinct of Wolfgang Feist to create passive house. I believe it was in the 80s when Europe was going through one of the energy crises they had. He asked himself the question, what if we could build a house that didn't need any heat at all? Well, he was a physicist, and he knew it could be done. He developed a mathematical formula, as we all know as the PHPP, using these 5 principles of airtight enclosure, thermal envelope, no thermal bridging, high-performance windows and doors, along with balanced ventilation and heat recovery, to ultimately create a house that operates like a thermos, a very high-performance thermos. Now, a lot of passive homes, some areas of the world, don't need any heating or cooling. Other places of the world, like Canada, or in the tropics for cooling, reasons of cooling, require heat, but very minimal, very little heat. That's the first half of the presentation. So here, second half, we have 12 projects. So 12 projects we're going to go through. Some things that our company has learned through these 12 projects, different climate zones, different things they take into consideration, and hope you get something out of this. Okay, first one, top left, in Georgia. Very high humidity zone, heat and high humidity. Ultimately, this project signifies the importance of performing a WUFI analysis. Now, WUFI is a German acronym, not going to try and pronounce it, but is very important for those of you who haven't heard of it, used to simulate hygrothermal performance of building envelope assemblies over time. So basically a model where building envelope where the designer is able to determine if the building envelope, if the vapor open membrane on the specific side of the building and the materials that are used that go into the envelope, making sure that it's able to stay dry or keep a building envelope system dry over time. Now, our standard open permeable membrane as a company is on the outside of the building. And even though Georgia experiences high humidity and heat for most of the year, there's also a long period of drying where we were able to keep our outside open permeable membrane in place. So very important. We're very lucky we have WUFI. Next, McCall, Idaho. High snow loads, almost 3 times the snow load that Ottawa has, over 150 pounds a square foot. This project indicates the importance of a 2-part roof system. So separating the insulated roof system from a substructural roof system over top that's there really to provide overhang support and operate as an indirect air cavity if required. Now, we're used to a standard secondary roof system being approximately 4 to 6 inches thick for most snow loads. But in Idaho, we had to increase that somewhere between 10 to 12 inches. Also, the owners of this project wanted deep overhangs and wanted to keep the snow as far away from the building as possible. So thicker overhangs as well. And another interesting part of this project was a non-concrete floor system. So we learned a little bit here. There's no basement in this project. Typically, it would be a concrete slab on grade, but the owners wanted to minimize the concrete. So we used a system that had 2 layers of laminated plywood over top of insulation, over top of a gravel drainage membrane, and we were able to provide a concrete-free floor system for these customers. Next, Snowflake, Arizona, extreme heat environment. This ultimately signifies the importance for flexibility in building envelope systems, for varied insulation levels, also varied vapor barrier placement. This house, even with all of that glass you can see there in the southern facing wall, was still able to achieve passive standards, and we could drastically reduce the building envelope in terms of insulated value than we would more typically use here in Canada. The wall systems for this project still needed to be somewhere between an R40 to an R45, and the roof somewhere between an R65 and an R70, meeting the passive house requirements. Next, Fieldbrook, California. High seismic zone. So when you're building in seismic zones, of course, a lot of extra strength is required. And this project signifies the importance of doing a 2-part wall system. So separating a structural wall component from a passive envelope, because there's a lot of extra framing, a lot of extra structure that's going to need to go into the structural part. So being able to entirely isolate that and have flexibility with that outside passive envelope to be able to hit the insulative targets where the project may be located. Even McCall, Idaho was in a seismic zone. So flexibility for a 2-part wall system, very important in order to build in all climate zones. This house in California was also in a forest fire prone area. So forest fires, lots of you probably remember the forest fire in Altadena, California, not too long ago. We've started design for a lot of customers from Altadena. And one thing I learned, I was talking to a couple, and they were explaining the situation to me. They told me, that not a lot of people know this, but our house wasn't in the fire. It was actually very far from the fire, almost 50 miles away. The wind carried blowing embers all of these miles away, and what happened is these blowing embers got into people's soffits. They got in through the roof systems, all the exhaust vents that would be typical in non-passive buildings, and all these houses burnt from the inside out. It didn't matter if houses were built with concrete walls, any type of construction, houses were decimated. And one way that Passive House easily protects against that is, of course, with the airtight envelope, high reflectivity sidings, non-combustible sidings, very important as well. But there's also soffit vents that you can install in your system that will automatically close and shut off roof ventilation through the indirect air cavities that would be typical to most passive buildings with being heat activated. So the mono-pitch roof system, low-slope roof systems, having the ability of those to simply integrate these soffits that can close at high temperatures easily solves the fire problem, or mostly solves the fire problem. Also putting the air intake and exhaust for the ERV systems on the leeward side of the building, so it's less impacted by wind. Next, Ottawa, Ontario. It's a picture of our recent demonstration home. We just had certified by the Certifiers Cooperative. Great group to work with out of Oregon. And this house, so certified Passive House Plus, but the overall intent of this project was to communicate affordability. It's compared to our original demonstration home we built about 10 years previous, which was a larger house, a 3,000 square foot home, ultimately built for holding a lot of people at open houses, 4-bedroom home. But after COVID, we've seen the cost of construction rise, right? Our original demo house, 3,000 square foot home, we could have built a dozen years ago for $200 a square foot, $180 a square foot most of the time too. But the building cost today, almost 50% higher, $300 a square foot. So building this house, reducing materials as much as possible, following a minimalistic approach to design. The window and door component was minimized as much as possible, where we are still designed to hit the passive standard, but we didn't put any more windows than was required for maximizing affordability. Also, for reasons of storage, we integrated storage shelves over top of the closets, washroom spaces, so that we didn't have to build any additional room for reasons of storage. And storage shelves over the closets and the washrooms, we gained about 200 square feet of space. So maximizing affordability. Next, Wakefield, Quebec. You can see in the background the ski hill. Interesting fact about ski hills I learned, for those of you who don't know, they usually put the slopes on the north side of the mountain. I thought was really interesting. You know, it's important here in Ottawa because the hills are really small. It actually extends their ski season quite a bit. But ultimately, with this project, very steep lot situation, and signifies the importance of having foundation systems easily integratable with above grade wall systems. On the right side of this picture, you can see the steep slope basically built into the side of a small mountain. We had to actually extend the foundation approximately 50% of the way up, which would have otherwise been the above grade wall system. So design consideration and take into place. Passive House proves you can build on any slope of property. Okay, Colville, Utah, high elevation and remote access for this project. We learned that with respect to windows and doors, interesting fact, whenever you're above 6,000 or 7,000 feet, the atmospheric pressure differential is so significant that it can cause windows to shatter unless special valves are placed in the glass during transportation and installation. So most glass is manufactured facilities closer to sea level, where the pressure is a lot higher. And when these windows are installed, lower pressure outside the glass at higher elevations. So these valves are needed to release the pressure and prevent the windows from bursting. So very interesting fact. This project was a prefab project, and we also had to modify the panels so that they could easily be offloaded and carried in with small trailers on pickup trucks. Okay, so modifying design for different property situations, very important. Next, Brockville, Ontario. This house has a western-facing front wall. The owners had a Mediterranean architecture-inspired design they wanted to roll with. They wanted a lot of glass. Problem was that wall was facing west. This house, though, was still able to achieve passive standard. Now, when we first put this through the PHPP, I believe the cooling demand was somewhere between 50 to 60% above the cooling load limit. So we did a bit of a strategic window reduction. We reduced the windows as much as possible. The owner's still being happy with it. And we played around with some window coverings. So what ended up happening is we had to put window coverings over those lower two glass sections in the middle and the top right glass section. Only those three windows needed a complete window covering, and instantly the cooling load was 25% less than the standard. Also interesting fact that for those of you who don't know, through the PHPP, interior white window blinds can reduce cooling load up to 30 to 40%. But in this case, western facing, you think about, or if you've heard about Passive House in Australia, Passive House in Australia is taking off as much as it is in Canada. It's interesting for me, when I've listened to it, you compare the reasons. They're doing it for reasons of cooling mostly, where we're building passive mostly for reasons of heating. And the simple strategy is reduce the window and door size as much as possible in Australia. But they cover the windows with exterior shading devices so that they're able to block 100% of that sunlight, so that direct sun's not coming inside. Okay, next, North Pole, Alaska. This is an actual town in Alaska, for those who haven't heard of it. And it's just about partway up Alaska. Very extreme cold. Temperatures are known to drop around minus 45 degrees Celsius every winter. And they don't stay this low every winter, but they are minus 45 for approximately a 4 to 6 week period. And so, this project signifies the importance of having flexibility in the building envelope to be able to accommodate thicker insulation in the wall system and the roof system. But most importantly, the ERVs that are used, the fresh air systems that are used, very important that they're able to work with the extreme cold as well. So there's certain passive ERVs on the market that use a geothermal loop to preheat the incoming air. There's also electric preheaters possible. Also, ability for a lot of ERVs to go through a regeneration cycle so that the machine can defrost itself during these extreme cold conditions. So this project highlights passive is possible, but research done, ERV, making sure the right mechanicals are obviously chosen for the proper climate. Next, Manchester, Michigan, contractor turns a page. This is a great story to tell customers. This contractor, I'll call him Bob, for 30 years. He's over 65 years old. He didn't want to change his way of doing things, but his son was a big part of convincing him, this is the way forward, Dad. So things went from being too complicated, too unnecessary, to by the end of construction, he was actually showing off blower door test results like they were fishing trophies. And now he insists that every home he builds be passive. Okay, and what's interesting here is they actually learned that a passive house is much simpler to build. They told us this. The house is much simpler to build than a conventional home, conventional subdivisions. When we build passive, of course, we have to take fine attention to the detail where wall systems integrate with foundation systems, roof systems, and those connections need to be extremely simple for the reason of airtightness. It's essentially impossible to make a lot of conventional buildings vapor tight, airtight because of complicated connection or ultimately connection details that don't exist. So this project greatly highlights people don't change because you convince them. They change because they experience it. Next project, Ottawa, Ontario, a highly shaded urban lot. So this project here, it actually looks like there's a lot of sunlight on the left wall and the right wall of this building, but it's actually in a densely packed urban environment, very little sunlight. This house was still able to be certified Passive House Low Energy. It was certified last fall by the Certifiers Cooperative as well. On the right side of this photo, you can see a picture of the neighbor. And this neighbor's house is about 20 feet tall. It's about 12 feet away from the southern wall of the building. There's large trees that surround the house as well, very tiny lot, very little solar gain in the wintertime. All we had to do is increase the thermal envelope approximately 15 to 20% and reduce the size of the windows to the point where the homeowners were happy with them and was able to achieve. So a great example of how passive house standard is achievable anywhere, regardless of climate zone, regardless of shading. Passive home is not a passive solar house. You do not need any sunlight. So this project highlights that. What I found is most interesting, though, is the customers, they still went forward and net zeroed the house on the net metering program. And this house produces all the energy it needs with a small 7 kilowatt solar array. And this is a great example of the project as well. Net zero on the net metering program. So it produces all the energy it uses for primary energy with a small 7 kilowatt. That 7 kilowatt only takes up about 30% of the roof space. And I think this is one item that's not spoken about at all, or not appreciated when it comes to net zero buildings and passive. Net zero buildings only make sense if they're passive, because a typical net zero home, and this is hypothetically thinking that, the way that the government is saying the standard is going to be to the net zero building code when it comes out, is a house approximately 50% better than code from a heating and cooling perspective compared to 90% better than code for passive. So net zero homes built to the lesser standard are going to require a lot more roof space for the solar panels. If that was the case with this project would probably not be able to be net zero. But because of the substantially reduced solar array, they are able to strategically place those solar panels on a small part of the roof that was unshaded for most of the year when the sun is high in the sky. It's a great example. Next, lastly, bottom right, the Caribbean island of Curacao. This project's going to be our first project in a tropical climate. This project signifies the importance of building envelopes needing to be vapor open or have the ability to be modified to be vapor open on both sides. So when you're building in a tropical climate, very important that the exterior is zero permeability, as close to as possible, or it's best for the building envelope if it's zero perm. Tropical environment, maintaining comfort conditions on the inside would still require the use of a ERV system, a dehumidifier. So dehumidifier would be part of this equation in addition to the ERV and cooling, of course, but each one of those machines with respect to dehumidification and cooling probably only need to operate somewhere between 3 to 6 hours a day, depending on the time of the year. So at the beginning, I asked you why you are here. Maybe now the answer feels a little more grounded and a little more powerful. You're here because you care, not just about how we build, but why. You're here because you believe buildings should heal, not harm. You're here because you know the future isn't found, it's built. And because somewhere along the way you decided that good enough wasn't good enough. And today you've proven something important. That this movement, the passive house community, is full of people defying the odds, rethinking what's possible, and quietly reshaping the world. This isn't just a job, it's a purpose. And today you've shown that this passive house community is made of people who aren't just talking about change, they're building it. So wherever you go from here, design like it matters, build like it lasts, and live like your work leaves a legacy, because it does. You're not just part of Passive House, you're part of the reason it's becoming unstoppable. And together, we're not following change, we're leading it. Thank you.